How does magnetic permeability affect electromagnetic fields? Imagine you have a magnet and a piece of metal. The way the magnetic field interacts with that metal depends a lot on how easily the metal can become magnetized. That property is called magnetic permeability. It tells us how well a material responds to a magnetic field. When we look at electromagnetic fields, magnetic permeability plays a big role in shaping how strong and spread out those fields are. In electrical engineering, magnetic permeability is a key factor when designing devices like transformers, inductors, and electric motors. These devices relying on magnetic fields to transfer energy or generate motion. The equation that links magnetic flux density, magnetic field strength, and permeability is simple. Magnetic flux density equals permeability times magnetic field strength. This means if you keep the magnetic field strength the same and increase the permeability, the magnetic flux inside the material gets stronger. Materials with high magnetic permeability, like iron or certain alloys, allow magnetic fields to become much more concentrated inside them. When you put such a material inside a coil with electric current running through it, the magnetic field inside the coil becomes much stronger than it would be with air or a vacuum. This happens because the tiny atomic dipoles in the material align with the magnetic field, boosting the overall magnetic flux. Permeability isn't always a fixed number. In many cases, it can change depending on how strong the magnetic field is. For ferromagnetic materials like iron, when the magnetic field gets very strong, the material reaches a point called saturation. At saturation, increasing the magnetic field no longer increases the magnetic flux proportionally. This nonlinear behavior is important to consider when designing magnetic circuits, because it affects how efficiently they operate and how much energy they lose. Another important concept is relative permeability, which compares a material's permeability to that of free space, which is a vacuum. For example, air and vacuum have a relative permeability of 1. Iron, on the other hand, can have a relative permeability of several hundred or even thousands. That means an iron core can support a magnetic field hundreds or thousands of times stronger than an air core for the same amount of current in the coil. Faraday's law states that changing magnetic fields induce an electric voltage in a circuit. The amount of magnetic flux linking the circuit influences how much voltage is induced. When a core material has high permeability, it increases the magnetic flux for a given current. This means that when the magnetic field changes, the induced voltage is larger, making devices like transformers more efficient at transferring energy. In summary, magnetic permeability determines how easily a material becomes magnetized and how it influences electromagnetic fields. High permeability materials concentrate and strengthen magnetic fields, which is essential for the operation of many electrical devices. Understanding how permeability works helps engineers design better transformers, inductors, and motors by controlling how magnetic fields behave in different materials.